Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College in the middle of Silicon Valley. And it's a great pleasure for me to welcome everyone here in the Smithwick Auditorium and everyone listening or watching us at home on the web to this lecture in the 14th annual Silicon Valley Astronomy Lecture Series. This is a free public program co-sponsored by the Foothill College Astronomy Program, by the Astronomical Society of the Pacific, by the NASA Ames Research Center, one of the great NASA centers in the country, and by the SETI, the S-E-T-I, or Search for Extraterrestrial Intelligence Institute. We appreciate their support. We encourage those of you watching the program to seek out information about our sponsors. These lectures always feature well-known astronomers talking about exciting topics in astronomical research, and we certainly have that for you tonight. Our topic is monster black holes, what lurks at the centers of galaxies, and our speaker is Dr. Chung-Pei Ma, a professor at the University of California at Berkeley. She is professor of astronomy at Berkeley, and her research interests include the origin and large-scale structure of the universe, some of the largest questions humans can ask. She also works on the formation and development of galaxies, and as we'll see tonight, on the growth of giant, hungry black holes. She is also, by the way, an avid violin player and pursued parallel studies in physics and music at MIT and the New England Conservatory of Music. So here, a Renaissance professor, to be sure, to talk to you about monster black holes, it is a great pleasure for me to present Dr. Chung-Pei Ma.
Okay, thank you, Andy, for the introduction and for the invitation to visit this lovely campus. So today I would like to talk about black holes. Now, black holes are ubiquitous, as I will try to convince you today, in the universe, but also in the pop culture. So let's just start out Googling black hole on the website, and these are some of the film industry's attempts at making black holes familiar to us. And this is a Disney production. In fact, we have Event Horizon in our Netflix queue at home, but it has only 1 star by the Rotten Tomatoes rating. So it just keeps sitting in our queue, and we are always able to find a 1.5 star, obscure, incomprehensible French film whenever we're desperate for something to watch. So I have to confess, I have not watched the Event Horizon yet, but I would like to see it at some point. And I see some younger audience here. I don't know what these things are, but it showed up when you Google black hole and look for images. There's some cars, summoners, and if you try to read these things, it reads like English. I have no idea what it's talking about. And for those of us who are old enough to have actually physically touched a machine like this, I assume these are virtual these days, or kids have all moved on to much fancier things. Pinball machines, if you can read here, this says black hole, and there's a captive hole, I don't know what that is, and clearly this has fascinated a lot of people. But let's first ask, why is a black hole black? Where do black holes get their name from? Clearly, it's not something we can see. It's black. It is really literally black. So let's start out with a simple concept called the escape velocity. Okay? So basically, gravity is attractive. So gravity has this fatal attraction. If you would like to escape it, you need to satisfy certain criterion. And this is Earth, and as we all know, by launching satellites or spaceship, that you need to give enough oomph to send it off. If you wanted to be a communication satellite, for example, or the Hubble Space Telescope, orbiting the Earth, then you will give it enough energy, but it will orbit the Earth. It's still bound to the Earth. But if you would like to go off to explore Venus, Mars, Pluto, or beyond, then you would like to escape the gravitational attraction of the Earth. So you need to give it more oomph to go on some sort of unbound orbits. And the key equation, and this is the only equation I'll show today, gives you the escape velocity, the speed you need, the minimum speed you need to escape an object's gravitational pull. And as you can see, it's related to g, which is a gravitation. It's just a constant, a number. And mass, m, is the mass of the thing you're trying to escape. So in this example, it would be the mass of Earth. And r is a radius of that object. In this case, would be radius of Earth. So if you can send your spacecraft up with a speed equal to this or greater than that, then you have a chance of going beyond Earth. And we can put in numbers. We know what g is. We know what m is. We know what r is for the Earth. And you can do the same thing for the sun, and you get the following numbers. We like to use kilometers per second, but miles per hour is much more familiar to us. So in order to escape Earth, you would need 27,000 miles per hour escape speed to get out. For the sun, the mass, of course, is a lot bigger, and the radius is bigger, but the mass is relatively bigger than the radius compared to the Earth, so you would need to launch 1.4 million miles per hour for your initial rocket to escape the sun. So what does this have to do with black holes? Well, let's go back to pop culture again. Okay, again, escape velocity has fascinated the film industry, and there are these movies. We didn't even bother putting this into our Netflix queue. It looks a little scary. Okay. But now we can ask the following question. Again, the same simple formula is up here, and you see this V. So you can ask the following question. If we try to go to a place, okay, or let's fix our object, a given mass. Let's say we have giant alien hands trying to shrink, say, the Earth. Let's squash it. So the mass remains fixed, but let's shrink r. So you can see, since the denominator shrinks, this number is going to get bigger and bigger. Okay, so as I shrink Earth, the escape velocity will increase and increase, until we hit the speed of light, which according to Einstein's special theory of relativity, c is the ultimate speed. You cannot go beyond c. c is the fastest anything can go, even if you had no mass. Nothing can go beyond the speed of light. So let's shrink our r until v becomes c. And c, in this case, is a constant. In vacuum, it's huge. It's 1 billion about miles per hour. Then, what's the consequence? So I will take Earth. Let's try to squash it. Then, since even speed of light, when you reach the speed of light, even light cannot escape now, because light travels at the speed of light. Then you obtain a black hole, because whatever light is trapped in there, even light itself cannot escape the gravitational pull of this thing I squashed. Okay, so that particular limit is what defines a black hole. Let's look at the same formula again. Okay, again, the same simple but very, very important formula. Okay, so again, I'm now setting v to the speed of light, c. Then I just move the equations around. Okay, so all I have again here is a mass of my object. Now I've shrunk it to the radius r, at which the escape velocity becomes c. So you really need to reach speed of light in order to escape, meaning you can't really escape. Then let's look at what is that number. Okay, that particular radius. How much do I need to shrink Earth before it becomes black? That is, light cannot escape. And this particular number, as you can see, C is a constant, G is a constant, both are numbers, and M is the mass of my object. So I can calculate this number. And this number is called the Schwarzschild radius, and often we use this to refer to the radius of a black hole, or the size of the event horizon. Now, I put the radius in quotation marks here because this is not a physical radius. Black hole is really a singularity. The gravity is so big that material got crushed practically into a point. There's some quantum fuzziness to it, but I don't want to get into that today. For purpose of today's talk, think of black hole as literally a point in space-time. Okay. Then the radius really is not a physical boundary, not like the radius from the Earth, but it's the radius within which even light cannot escape. So it's a special region in space around the black hole that you would not want to get into because that's the path of no return. You will not be able to get out. Okay. And you can see this radius depends on the mass of the black hole. The bigger the mass, the bigger this radius. Okay, and that's the size of the event horizon. So let's put in some numbers to see how big this event horizon is for various masses of a black hole. Okay, so you can see the picture here. Basically, here is the actual black hole, a singularity, but there is an imaginary boundary within which the sphere, you're doomed. And if you were to be so curious to design a spacecraft to study a black hole, you would like to circle around just hovering beyond the event horizon. Then you're safe. So let's look at some of these numbers. Okay? So as I said, the more massive a black hole is, the larger the event horizon is, and the larger the volume that you would not want to get close to. So they become more and more monstrous. And I'll be talking about some of the biggest black holes we know today. But before getting there, let's look at a few numbers. They're interesting. So for the example of the Earth, if we were able to shrink it, the Schwarzschild radius, or the size of the event horizon for Earth mass black hole, would be 1 inch. Okay, so it's fairly safe. Just don't get within 1 inch of a black hole. That's of Earth's mass. But if this were a solar mass, a sun, say we squash the sun into a black hole, make it really, really dense so that it became a singularity, then the event horizon, the size of the event horizon is about 3 kilometers, 2 miles. But today I'm going to talk about 10 billion solar mass black holes, on the order of that. These are the record-breaking black holes we've found recently. So you can easily scale linearly. So the size of the event horizon is approximately 5 times the size of the solar system. Okay? So in pictures, this is one of the publicity slides we had when we made the press announcement a couple of years ago about the discovery of these black holes. I'll talk about where they are. They tended to live at the centers of galaxies. So if you zoom in there, this is actual image. This is an artist manipulation rendition of an actual image. So this would be the event horizon of a 10 billion solar mass black hole. And to just give you a sense of how big that is, a solar system would fit right inside of that. Okay. So that's how big the point of no return is for the biggest black holes in the universe. So let's now turn to another question. Now, where are black holes found in the universe? And here I'm talking about astrophysical black holes. And there are 2 primary sites where we astronomers have found evidence for black holes. The first type of black holes is really the result of deaths of massive stars. And this is not the type of black holes I'll be talking about, but they are very fascinating topics, so I would like to just spend a minute on that. As many of you know, that stars, like people, they have births, they have midlife crisis, and they die eventually when the hydrogen, the fuel at the center that's powering the light, eventually run out. Our sun is an ordinary star. There are billions and billions of stars like that. It's about midlife, so it's going through its midlife crisis. It's about 4.6, 5 billion years old, and it has another about 5 billion years to go before it dies. Now, how a star dies depends on its mass. And there are three types of stellar graveyards. Our sun, which is relatively puny, will die fairly gently. And at the end, when the hydrogen, helium, and so on, the fuel get used up to fuse into heavier elements, the sun will become a white dwarf. It's an Earth-sized dense object. But stars, more massive than the sun, there are fewer of them, but we have seen quite a few of them. Could be 10 solar masses, even up to maybe 100 solar masses. These massive stars are extravagant. They are massive. They contain huge amount of fuel. So they got a lot of money, but they spend their fuel at an even faster pace. So they use up their fuel very quickly. So contrary to intuition, massive stars actually live very short time, and they die spectacularly, unlike our sun. And when they die, there are two options, depending again on their mass and the process of their mass loss, their dying procedure. They could end up as a neutron star, which is an even smaller, denser object of primarily made of neutrons, or even more dramatically, as a black hole, if there is no pressure to resist the final gravitational collapse. So if the star initially were 10 solar masses or beyond, very likely they will end up as a black hole. And the best evidence for a stellar mass black hole, the end stage of a massive black hole, is this binary system called Cygnus X1. And this is an artist's rendition. It's sitting here, but it has a binary normal star that's giving out light. So since it's a binary system, we get a lot of information about the system. We can watch what this star is doing, and this black hole is giving out copious amount of X-ray emission, very energetic photons that's being accelerated as they plunge into the event horizon of this black hole. So the measurement of its mass had been done quite remarkably well by now. And the current estimate is 14.8 times that of the sun, mass of the sun, 14.8 solar masses. And there are numerous other examples of such death of massive stars. And they are sort of everywhere in our galaxy. There are not a whole lot of them, but there are tens of them, and other galaxies. As long as you have massive stars, they will die massive enough, they will die as black holes. But today, I would like to talk about the even more exotic variant of black hole. And these are sometimes referred to as supermassive black holes. And supermassive, I really mean pretty massive things. I'm going to talk about things of millions to 10 billion solar masses. And they live at special places, as far as we can tell. And typically, we seem to be finding them at the centers of galaxies. Okay? So our Milky Way is obviously our most familiar galaxy. We live inside of the Milky Way. And this is an actual image in the infrared of our home. This is taken by the COBE satellite, which was the satellite that discovered the cosmic microwave background anisotropies in the early 90s. But it also had a different instrument in the infrared that took beautiful pictures of our own galaxy, for example. So you can see that it looks very flat. Okay, we're viewing our galaxy obviously as young. We're not living at the center. We're not living at the center anywhere as far as we know, not even our own galaxy. And we're looking toward this image, looking towards there is a spheroidal shape of stars towards the center of our galaxy. So the way to think of our galaxy is basically we are an olive on a pizza, but close to the edge of the pizza. And here's a view looking towards the center of our pizza. Okay. And the best measured mass for a supermassive black hole is the one lurking at the center of our own galaxy. And its mass is estimated to be about 4 million solar masses. But this is really on the very, very small side of the black holes I'm going to talk about. Okay. So the one in our own center of our Milky Way, and this is another image in the near infrared taken towards the very crowded field towards the center of our own Milky Way. Without this arrow, no one can tell where the center is, obviously. But we have various other wavelengths in the radios and X-rays pinpointing a point source that's giving out enormous amount of energy. Okay? If you're curious where this is, look for the constellation Sagittarius. Some of you probably have that as your sign. Okay, and it's in the direction of the constellation Sagittarius. And this particular object at the center is called Sagittarius A star. But black holes, by definition, I just talked about, are black. So how do we observe them? You can't see them. So the standard trick is we use things that are luminous, gas, stars, anything that emits electromagnetic radiation, very, very close to the black hole as the probe, as the tracer. When they get very close to the black hole's gravity dominates, so their motion will be largely influenced by the black hole. So we can use the motion of these tracers, luminous tracers, to infer its mass. Very much like how you can use Kepler's laws to infer the mass of the central object that you're orbiting about. You can use Earth and the planetary orbits to infer the mass of the sun, for example. Okay. So here is, by the UCLA Andrea Ghez group, an actual movie of several dozens of stars that are traveling, orbiting around some curious point. Again, the star, obviously, we put that there. All we can see are the motion of these stars. And this is really a painstaking, incredibly state-of-the-art kind of observations, because as you saw, the Galata Center is very, very crowded. The optical light is hugely obscured by dust. It's very opaque, like very polluted city. Okay, so it requires adaptive optics and special techniques in order to trace the orbits of individual stars. And you can see these data are taken over almost 2 decades by now. And I think at the end, it's highlighting the orbits of 3 stars that have actually completed their orbits. Okay, remember, this is in projection, so there's a 3rd dimension that we can't see from here. But this is an incredible amount of information that we can use to reconstruct. Basically, if there were nothing at the center, these stars should not be all orbiting, right? A star going in some direction will just keep going unless there's something pulling on them. As you can see, they're all bending over about something in the middle that we cannot see. And you can use these orbits and fairly simple calculations to infer the mass of the thing that's making them bend, the orbits bend. this is my favorite one. You can see how it's a highly elliptical orbit. It's getting very close to the black hole and then coming out. Okay? If there were nothing sitting here, there's no reason for it to be pulled back at all. It should have just kept going. Okay? So this is the best system for us to study a massive black hole. And by using these orbits, that's how the 4 million solar masses I mentioned were obtained. And there are two groups right now doing UCLA's one, and Reinhard Genzel's group in Germany is another one doing this kind of measurements. Okay, so now let me take you beyond our Milky Way. There are billions and billions of galaxies out of our Milky Way system. And again, our Milky Way appears to be an extremely ordinary galaxy. There are many galaxies like our Milky Way, and there are many others that are more massive, less massive, and so on. So beyond the Milky Way, probably the most fascinating galaxy that had been seen to host a black hole, supermassive black hole, is this Messier object 87. Okay. And this was cataloged in Messier's work hundreds of years ago, a French astronomer. Back then, no one knew about galaxies or things like that. He was looking at nebulae, these fuzzy things through his little telescope that were nuisances to him. So the Messier catalog right now such a famous thing is actually a nuisance catalog in the sense that he was looking for comets. So he only cared about fuzzy things that's moving from night to night. And he found all these annoying fuzzy objects that did not move. And he knew those were not comets, so he cataloged them and ignored them. And today we now know M1, the first object, for example, is the Crab Nebula. M87, for example, is a giant, giant elliptical galaxy. Okay? And this is a Hubble Space Telescope image of M87, which is an enormous, much bigger galaxy than our own. It's not shaped like a pizza. It's shaped more like an ellipsoid, a boring sort of ball-like, but giant collection of stars mostly. But at the center, and you can see this jet coming out, and there a lot of work had gone into this to infer the mass of the black hole inside. And I'll come back to the method momentarily. But this was the record holder at about 6 billion solar masses before the two we discovered a few years back. Okay, so just to highlight a few other very interesting galaxies in the universe that are believed to harbor black holes. This is an active galaxy called assente, and this is a ground-based image, and this is a Hubble Space Telescope image. You can see a very complex collection of gas and dust lanes. The black part doesn't mean there's nothing there. In fact, it's because the light is obscured by dust. Okay? And this is in the optical wavelengths, but the Chandra satellite in the X-rays had taken picture of the same object, and again, see this enormous jet coming out. I understand that Professor Roger Blanford had been here earlier this year or last year and talked quite a bit about these jets. And again, our current understanding is a black hole is needed in the center to suck stuff in and then spew things out right outside the event horizon and coming out to accelerate particles to such an enormous energy and speed. Without the black hole, it's very difficult to explain the existence of these jets. Okay. And let's just look at another example. Okay, so not only do we think that nearby galaxies, it seems like at the center of most of these galaxies, we seem to find evidence for a supermassive black hole. There are also a few systems in which we think there may be binary black holes, two massive black holes orbiting each other. As probably many of you know, our sun is a very rare example, right? If you look at stars in our galaxies and elsewhere, more stars are in binary systems than a single star. So imagine if we had 2 suns to deal with. Wouldn't that be really fascinating? Maybe a little too hot. But most stars like to form binary systems, and perhaps similarly for black holes. Okay, so this is another famous galaxy. This is in the optical wavelength. This is called NGC 6240, and on the left is the Hubble Space Telescope optical image, and on the right is a zoom in again in the X-rays. And of the very center, and there are 2 peaks of enormous amount of X-ray emission, again, very energetic photons believed to be powered by the gravitational accretion of black holes. And these 2, we think these are good candidates, okay, they're not confirmed, that at the center of each of these blobs of X-ray, there's a black hole sitting there. And based on our current understanding of how galaxies form, this is not perhaps that strange. The way galaxies form is not through just sitting there collecting stuff and collapsing and forming a collection of stars and gas. The universe is a little bit more dynamic than that. We think galaxies perhaps form primarily through mergers with each other. Our nearest neighbor galaxy to us is the Andromeda galaxy, Messier Object 31. Even though the universe is expanding and accelerating, our neighbor, in fact, is moving towards us due to the local gravitational pull, our perhaps too friendly neighbor. And we are on a collision course. M31 and the Milky Way will collide in about several billion years. And inevitably, because the gravity is pulling the 2 close to each other, and when the 2 galaxies come together, and dramatic things will happen. We can do a lot of numerical simulations to see what happened to that. And we believe the stars will scramble, the gas will trigger new stars to be formed, and eventually it will settle down into a bigger galaxy. Okay? And during that process, our own black hole and M31's black hole, which we think there is one, there's pretty good evidence for that, will invariably come together to form a gravitationally bound system that's quite energetically favored. And then this perhaps is a snapshot of something that may happen to our neighbor and us in a few billion years. What happens to them subsequently is a very interesting open question. You need to really lose a lot of energy and angular momentum for the 2 black holes to actually coalesce to form a bigger black hole. And how long it will take for that to happen is an open question, but some people believe that there's a very high chance for them to actually come together and to grow, to become a bigger black hole. Okay? So that's how black holes perhaps get bigger and bigger too, is by merging with each other and getting more massive. So I just show you some interesting examples of galaxies that are believed to host black holes of various masses, and perhaps even binary black holes. So let's ask a little bit more about, so how do we find them? Again, back to the question that black holes are black, so we need to really look at the tracers around them to infer its mass. So I show you the beautiful picture of the Milky Way, the stars we can actually trace individually. Unfortunately, when you go beyond our own galaxy, the Galata Center, to these external galaxies, there's no way we can see individual stars. These galaxies are way too far for us to see the individual orbits, so we need to study them collectively. Okay, so how do we find black holes? Well, in the beginning, sort of, why not? This is, it's black, right? Unfortunately, we don't have such beautiful images of the event horizon, not yet. Okay? So the ones we targeted about 5 years ago, starting about 5 years ago, is even beyond M87, is in a cluster of galaxies called the Coma cluster. It's one of the biggest cluster of galaxies close, I mean 300 million light years. Okay? And what you're seeing here is an optical image. You see basically blobs, right? It looks pretty boring, just blah, 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 blah. Now, each blob is an enormous galaxy here. This is cosmic scale we're talking about, okay? And you see two very bright, the biggest galaxies in this coma cluster. And each one we're talking about probably containing at least 1 trillion stars. Again, much bigger than our Milky Way. And then with the dark matter halo, a collection of dark matter that's probably at least 10 times more massive than that we cannot see by our own eye. Okay? And 4889 is the brightest one here in this cluster. And again, by eye, you can't really tell who is where, right? They seem to be projected together, but we actually can infer in the third dimension whether they are together physically, but not just projected on the sky. And galaxies, like humans, like to live in societies, like in cities. So if you look at galaxies on the sky, they're not randomly distributed. It's very much like a satellite photo of the night on Earth. You see pockets of city lights, right? And vast region of darkness. Same thing for galaxies, but the reason here is gravity. So galaxies like to collect together to form a cluster. And this is one of the best examples of a collection of many, many galaxies all living in one spot in the universe. It's called the coma cluster. So we targeted, this is a zoom in of the biggest, brightest galaxy in the coma cluster. Its name is NGC 4889, the catalog number. And we zoom into the very, very center, and we measured the velocities of the stars near that, and there we inferred a mass of the black hole of about 20 billion solar masses. So let me tell you just a little bit about how we go about doing this. So the telescopes we use are some of the biggest, basically the biggest available on Earth. For example, the Keck telescope atop Mauna Kea in Hawaii. And the Gemini, which is also there. One is 8-meter telescope. The diameter of the mirror is 8 meters, and the other one is 10 meters. And we also use special spectrographs. Basically, that will disperse the light to give us a spectrum for the light coming out from the galaxies. And we also turn on these things called adaptive optics, laser, something a little more powerful than this laser, to correct for the turbulence, disturbances due to the atmosphere, which make a star twinkle. Okay, that for astronomers, that's a very annoying thing to have. You really don't want the twinkling to blur our vision. So the fancy techniques called adaptive optics in real life can correct for that kind of blurring. So we get very sharp eyes, images, as good as the Hubble Space Telescope, which is orbiting above the atmosphere, which is not affected by the atmosphere. But we also get the advantage that the Hubble Space Telescope, the mirror, because it's way too heavy, is only 2-ish meters. But on the ground, we can use 10-meter telescopes. So it's a much bigger light bucket. So we can get a lot more photons using these ground-based telescopes. So it's a combination of huge telescopes on the ground with this very sharp images that allow us to pierce towards the very center of these galaxies, 300 million light years away. Okay, so I just want to mention one thing about why the centers of these galaxies are difficult to measure, why we need sort of the state-of-the-art equipment to do that. And the reason is, as I show you, this is one of the galaxies we looked at, and they're typically at hundreds of millions of light years away. Okay? And what we like to do is we like to measure the velocities of the stars. So here, we can't see individual stars, but we see a collection of them. So it's a bit like a swarm of bees. Okay, so when a swarm of bees is very close to our eyes, we can see individual bees going around, right? You can see them, and you can see them going around each other, and you can, if you have an instrument, you can measure how fast they're moving through Doppler shifts. But if a swarm of bees is very, very far away, you have no hope of identifying individual bees, but you can still measure their collective motion statistically. Okay? So for us, these stars are like a swarm of bees very far away. So I cannot draw for you individual orbits, but we can still measure the velocity distribution of these stars through the spectrographs. Okay? And as I mentioned, we need to go very close to the black hole, and for these galaxies, we typically need to be able to get the speed of the stars within about 1,000 light years from the hole, the center. Now, 1,000 light years sounds really far. It's a big scale. But when you put 1,000 light years at a distance, so I'm saying 1,000 light years here, at a distance of 300 million light years, okay, that's a very, very tiny region at that distance. So the analogy I could draw here is if we shrink 300 million light years to the distance between San Francisco and Los Angeles, okay, then we are sitting in San Francisco with a telescope trying to measure something happening in Los Angeles. What would that analogy be? The analogy would be roughly like having, say, Yo-Yo Ma in the Disney Hall in Los Angeles playing Flight of the Bumblebee, and we're sitting in San Francisco trying to measure how fast his fingers are moving. Okay, that's sort of the relative distance that we need to resolve. And that just requires sort of the good telescopes, good instruments in order to do that. That's roughly what we try to do. Okay. So let me just very quickly mention one fascinating thing that many of us are studying right now, and it's the fact that if you draw the black hole mass, I mentioned our Milky Way at 4 million solar masses. I mentioned COMA's brightest galaxy at 20 billion solar masses. So you can put them on a scale, make a plot of them, and you can draw the mass of the host galaxy, the mass of the Milky Way, the actual galaxy, or NGC 4889 or Messier 87. There's a very interesting correlation that bigger black holes seem to live in bigger galaxies. Okay? Of course, this is a cartoon picture. In real data, there's a lot of scatter, but over sort of factor of 10,000 in black hole masses, this overall trend is quite clear. Okay? So which is telling us that the black holes lurking at the center of galaxies know something about the much bigger host, the environment they're living in. And that to us is a very fascinating clue because it's telling us that we need to understand the growth of galaxies and black holes at the same time. Anytime you see any kind of correlation, usually it indicates there's something a little bit more profound behind these things. And that's one area of studies that many of us are doing. As we merge galaxies, maybe we merge the black holes, can we explain this sort of correlation as a test of our understanding of how galaxies and black holes were assembled? Okay, so now I just want to spend a few minutes coming back to black holes, not necessarily supermassive black holes, but just think about a few myths about black holes. People have been so fascinated by black holes, and we are often asked, should we be scared of them? It doesn't help that my title is Monster Black Holes, obviously. Okay, so let me just dispel a few of the myths, common myths. One is obviously black holes only exist in science fictions and Star Trek and so on. That we see a lot of that. But I want to just mention that really black holes are ubiquitous. Okay? It is predicted to exist by Einstein's general relativity in the sense that it's actually a mathematical solution to this equation called the Einstein equation that governs how matter and radiation warp space-time. Okay? And that equation, black hole, is a solution to that very complicated equation. Okay? So it's mathematically completely allowed, and if general relativity is correct, there's no reason for it not to exist. But of course, every time we talk about general relativity, we get the impression that it's really difficult, no one understands. I don't know, it's 12.5% or people or 13.5 people on Earth understand general relativity. Okay, that was the myth. Again, I wanted to dispel that myth in the sense that many advanced undergraduate students in our universities are taking general relativity these days, okay, and they enjoy it enormously. So it's really not that difficult, and it's really a fascinating subject to study. And I encourage you to look into that. It's really a beautiful, beautiful theory. So that leads me to the second myth, okay, that black holes are complicated. Okay, I just mentioned general relativity. It's really complicated, so black holes must be really complicated systems. I will argue not, in the following sense. A black hole is completely specified by 3 numbers. Okay, its mass that we just talked about could be 14.8, it could be 20 billion, okay, or anywhere in between. And its spin, how fast that hole can spin, and its electric charge. And you can prove mathematically that once you specify these 3 numbers, you're done. So another way to say it is, if I have 2 black holes here with identical mass, identical spin, and identical charge, they are indistinguishable. Can you imagine if 3 numbers could specify a human being? Wouldn't that be really curious? 2 people of the same height, the same weight, the same how fast you can spin on an ice skate. If you have the same numbers, you will be identical people. Okay, so in that sense, black holes really are extremely simple. Okay? And for the observations I just touched upon, like why those stars would be turning around, making that such a huge sharp turn, you could say, does it have to be a black hole? Like, could it be a collection of more ordinary stuff, stars or something that happen to be packed into that very center, but weighing 4 million solar masses? Okay, believe me, there are many, many papers written about that possibility. But in fact, any of those conjectures would be even more complicated than a black hole. How would you keep 4 million solar masses of individual stars hidden and stable? They like to merge or collapse. So in many ways, many alternatives to black holes that people have cooked up to explain that central 4 million solar mass would be even more complicated. So ironically, black holes are the simplest explanation for many of the observations I mentioned. Okay, another myth is that black holes are cosmic vacuum cleaners. Are we going to get sucked into a black hole? Should we stay away from that? Okay, and that's why I gave you the numbers for the event horizon. Here, only if you're near or inside the event horizon could you not escape, right? Outside of that, the escape velocity is smaller than c. We can't do that in practice yet, but in principle, you could launch your spacecraft with velocity v escape very close to c, okay? But when it's at c, you're doomed, okay? So matter is sucked in only within the event horizon. I gave you the numbers earlier, okay? Another way to say this is when you are very far away from a hole, the gravity is identical to having another object, which is not a black hole, of the same mass at the center. Okay, it doesn't matter. If I'm very far away, the general relativistic effects are not important. In fact, it's Newton's law, then I actually would not know what's at the center. Or another way to say this is that let's just replace our sun. Let's squash our sun into a black hole, as I say. Let's make its radius 2 miles. Okay, then it will turn into a black hole. Then if we were to do that suddenly to the sun, but keeping its mass, 1 solar mass at the center, the Earth's orbit would not change, okay, because there's the same amount of mass at the center, gravity, but of course it will be kind of cold and dark. Okay, so in that sense, we don't have to be worried about being sucked into the 4 million solar mass black hole at our Galata Center. We are at about 26,000 light years away. Okay, so that's way beyond the any kind of event horizon or sphere of influence of the black hole. Okay, so let me turn to the very last thing. I mean, I started this, so black holes are monsters. Well, in some ways, they are enormous, and a black hole, a singularity weighing 10 billion solar masses, that's more massive than many, many galaxies out there, okay? But I would like to say that black holes are perhaps friendly monsters. So I'd like to show you this drawing by our son when he was 3 years old. When we announced the discovery of the 10 billion solar mass black holes, he was in preschool. So he started to draw black holes. And this is the picture he gave me. And so I asked him, what is it? So he said, that's a black hole. It's a black. So I said, what are these things here? He said, well, I want to chain it. It's my friend. I don't want it to flow away. So I have these chains here, and here's the black hole. So we want to start you young, that black holes are fascinating objects. They're not scary, but just don't get too close to them. Okay, thank you.
If you were right next to a singularity, the equation you showed at the beginning, the square root of 2gm divided by r, well, in a singularity, r is 0 technically, but you can't divide by 0. So I wonder what the actual escape velocity would technically be.
That's a great question. Thank you very much. And you're not allowed to do that in the sense, sorry to say that, in the sense that you're absolutely right that, in the sense that equation really is true for an object with a mass and with a physical radius. So you can do that for the Earth, you can do that for the sun, and you could shrink it. But when you get to the limit of general relativity, you really probably should use the general relativity equations. As it turned out, by dimensions, any kind of speed will scale like that, gm over r with the square root there. I challenge you to find an alternative equation to that. But that factor of 2 also happened to be exactly what's predicted by general relativity. So in a sense, you can do that by taking the limit. But don't do that for the black hole itself, because that's already in the limit where that equation doesn't particularly hold. So you can use that to derive the event horizon of a black hole. Okay, so that R would be the event horizon, but not the actual size of the black hole. If you want to talk about something beyond singularity, as we heard recently from Stephen Hawking, then you really would like to put in some quantum mechanics to calculate the fuzziness of the singularity. But that's a great question.
So I'll ask about that equation as well. Obviously, the equation for Newtonian gravity applies to objects that have mass. And something that's implicit in your talk is that gravity also affects photons, which don't have mass. Can you say something that, without getting into the mathematics of general relativity, can you say something about just how that extension works?
Right, exactly. So the curious thing is, if you remember from Newton's law, that there are two masses. One is the mass of the object, the photon, and so on. You're tracking. So in this case, it would be the mass of the spacecraft, for example. And there, the other mass, the big M, which is the mass that you're sitting on. As you may remember, that little mass of the orbiting object cancels, right? F is equal to ma, and F is also equal to gmm over r. So that little mass cancels. That's exactly how Galileo showed that it doesn't matter in the absence of air resistance in vacuum, a feather and a rock will fall at the same rate. Okay. Same thing, take the feather to be massless.
So it doesn't matter if an object has
Exactly,
zero,
that
zero mass or
particular
very large
mass actually cancels even for massless things like
gravity. Well, I guess I just failed freshman physics. Sorry about that.
Okay, thank you. My question is about the differences between Newton's theories and some of the later theories. If you want to explain this, we know from Newton's theories that things will gain speed going in and lose the same amount of speed going out. So if you send something in from far away, it will actually be faster than the escape velocity when it gets closer, and then it will have that same speed fast enough to leave again. And I know that's not true. So can you explain the difference?
Wait, sorry, I couldn't hear part of your question. Could you?
Well,
repeat it?
this would be different than Newton's theories, right? Because in Newton's theories, you gain as much speed going in as you lose going out. So do you want to talk about the differences there at all? There's lots of ways to try to explain that, and I was wondering what your explanation is.
Well, so it's correct that energy overall must be conserved. Maybe that's what you're alluding to. But that doesn't mean that there's not a existence of event horizon, right? So you could be falling in, and at the same time, you're losing energy to the surroundings. But if you can calculate the total energy of the system anywhere in the universe, it must be conserved if you do your budget right. So in that sense, energy in is equal to energy out, but you have to be very careful by what you mean by in and out in this case. I'm not sure what you're referring to.
Okay. Yeah, I know there's classical coordinates and all that, and that's way too complicated to go into. So I've heard that it's not time reversible, that once you're in, there's no way out, and it's a one-way ticket once you're in, even though you're...
It's a one-way ticket, but the energy is conserved.
Right.
Isn't that great?
Because in general relativity, we're taught that it's a one-way ticket, and in Newton's theories, it's not, so I guess that's...
There is a lot of discussion about whether information is lost, okay? But that sort of touches upon a more profound level of quantum information and so on. And, we can, or entropy, what happened to the entropy of a black hole, whether it increases and so on. So in that sense, there is an asymmetry.
Thank you.
Yeah, but in terms of energy conservation, it's so far we have no indication that energy will be violated.
Thank you.
Let's move on. Quick question, perhaps my misunderstanding. I thought I heard you speak about a jet coming out of a black hole. Would you give us a little more information about that? Can something leave the black hole?
Exactly. So again, distinguish the region within the event horizon and above the event horizon. So there, all the jets are emitted well outside the event horizon. So there's a lot of, another thing I didn't have time to get into is the black hole outside of the event horizon, in fact, is impacting the gas in a very profound way. That's what we call feedback. That's how we think a lot of the galaxies we observe today acquire their current color, star formation, and so on, because the central black hole is impacting the surrounding gas. But all of that occurs outside the event horizon. Again, it's gravitational acceleration and so on.
But does it actually leave?
Yes, the jets, you saw that we can measure the Doppler shift. So they are definitely, in fact, they're moving close to the speeds of light away from the center. There are very good measurements of that.
Hi. So many questions and so many other people in line. So I'm hearing a lot about orbits, and I'm wondering, even with the supermassive black holes, the galaxies that surround them are also very massive. Does the black hole contribute, is the black hole a small percentage of the mass of the matter in the galaxy?
Yes, that's a very important question right now. We are trying to quantify. So that cartoon I show you, bigger black holes live in bigger galaxies. the horizontal axis, we could plot the mass of the galaxy. And so your question would be, what is the overall ratio? And definitely, it's measured to be about 0.3% on average. So the black hole is a tiny fraction of the mass of the galaxy. But its impact is really, really big on the surroundings.
Is the black hole, like, almost by definition, the center of gravity for the galaxy?
That's a very good question, too. Basically, if you have a black hole wandering around on the outside of a galaxy, it likes to sink towards the center due to a thing we call dynamical friction. It's almost like gravity has a friction. And given enough time, it likes to go to the center. But we are also wondering about, I mentioned these binary black holes, if they coalesce. One thing I didn't have time to talk about is the very final merger of two black holes. The space-time is so ripped up, distorted, that we believe gravity waves could be emitted at that point. And that's one of the last predictions of general relativity that had not been verified, the existence of gravity waves. It's very much like electromagnetic waves. In that case, you shake an electron, it emits electromagnetic waves. In this case, you shake, I take you, I shake you, you will emit gravity waves, but it will be so weak. But in the case of supermassive binary black holes, it will emit gravity waves. So what I'm alluding to, so we have great experiments out there, LIGO, for example, and pulsar timing that's trying to find this holy grail of general relativity. But when the waves get emitted, the final black hole coalesced will get kicked out because you need to conserve linear momentum. So there is a possibility that some of the black holes could be sent away from the center of the galaxy. And those would be very hard to find because in our case, we know where the center is, so we zoom in. In that case, it could be in the vast space in the galaxy, and a number of us would be very interested in looking for these wandering black holes. But for all the ones I've talked about that we have been able to measure, they seem to be at the center of the galaxy.
I have a question regarding the creation. When the universe was created, it started from a point of singularity. So I'm just wondering, it must have come from the previous universe, so it shrunk to a point of singularity. Is that something like a black hole phenomenon on a mega scale when the universe started?
In some sense, that is true. So the Big Bang is believed to be a singularity. It's not quite the Schwarzschild solution that I was talking about. And also, it's not, we know nothing basically about what happened before the Big Bang. So there is a possibility that the universe is cyclic. Okay, so maybe before this Big Bang, the universe was expanding and then contracting, went to a singularity and expanded again. And currently we have no way of knowing that right now because our laws of physics break down very close to the time of the Big Bang. But Big Bang itself is a singularity too. Sorry.
I wanted to say, when the thing is sucked into the black hole, doesn't that defy the second law of thermodynamics?
I don't know.
Because I thought energy could never be created nor destroyed.
People debate about that. The reason is thermodynamics is a classical theory, and thermodynamics in a curved space-time is not particularly well defined. So people debate about, the general belief is that entropy will increase or stay the same. We don't have any observational evidence for the violation of the second law of thermodynamics. But I think you should study physics and maybe come up with that answer.
I also wanted to ask, the edges of the black hole, those are obviously inside the event horizon. So don't they get sucked deeper and deeper into the black hole until it collapses into a singularity?
So remember, the event horizon is a fictitious surface. There's nothing there. You cannot touch the event horizon. It's just a radius. Okay, so there is nothing there that's associated with the black hole, but I could throw you into the black hole. And that's the case when you pass the event horizon, you're not gonna feel, oops, I hit something, as if you were hitting the surface of the Earth, but you're just gonna keep going in. But then if you were trying to radio me, sending a radio wave to me above the event horizon, you're just gonna keep going in and keep going in, and I can't rescue you.
But the black hole itself is inside the point of no return. So
The black
should-
hole is at the very center of the singularity, just a point.
Okay.
Okay.
Well, we know that black holes generate a gravitational field, and if gravitational fields involve gravitational waves, then could it be that gravitational waves are an exception to the rule that nothing can escape a black hole?
That is a very interesting question in the sense that gravitational waves are emitted during the final coalescence. So in the sense that it's still not within the event horizon. Okay, so there is no way that even gravity waves can come within that strict boundary.
Okay, thank you.
Okay. Gravity waves arise from distortion of the space-time around the black hole. Okay, yeah, but that's a very good question. Yeah, I don't think any information is believed to be coming out of the event horizon.
How about dark matter? Is there dark matter in a black hole? And can you make a very black hole out of just dark matter?
Yeah, that is a very, and that's another thing I study. I like to study things we can't see. And the answer is no. Black holes are not, at least not the kind of black holes I'm talking about. They are not candidates for dark matter. That's a great question. I mean, that's an obvious thing to ask. And the reason is these are all end states of a star or some ordinary matter. Even though the process sounds really dramatic and weird, when you collapse a star into a black hole, the black hole is made of whatever the star was made of, and to us, that's ordinary stuff. That's baryons, that's quarks, electrons. And you cannot make up dark matter from that kind of material. There is a tiny parameter space called primordial black holes, tiny, tiny little black holes existing in the very early universe. Those are not considered to be made of quarks. But currently, it doesn't look like there are enough of them to make up dark matter at all. So dark matter, the current candidate, is believed to be some kind of elementary particle that's in this room right now. I mean, don't you feel it? It's passing through our body. Okay, that's the current candidate.
Thank you. My question's actually somewhat related. I'm curious about the relationship of dark matter and black holes. First of all, in addition to ordinary matter that may fall into a black hole, presumably some dark matter also falls in. I'm wondering if the proportion of dark matter is roughly the same as the proportion one would expect to find in the mass. I gather that's about 7 to 1.
Right, that's an extremely reasonable question, and the answer is no. And I almost wrote a paper about it until I realized someone had written the same paper 20 years ago. And the reason really is not too difficult to think. In order to get sucked in, you have to get very close to the black hole, okay, as we were talking about. Like right now here, we're not going to fall towards the black hole. We're happily orbiting around the center of our galaxy right now. Okay, so that is to say you need to dissipate a lot of energy in order to get very, very dense. And dark matter, by definition, doesn't emit electromagnetic radiation. So its distribution is much more diffuse compared to ordinary gas, things made of quarks. So gas is able to get very dense through the loss of energy, radiation and so on. So they are the primary food source feeding these black holes. They're very hungry objects. They like to gobble up, and that's how they can emit these jets, because they're fed huge amount of stuff. But that food source is primarily gas, because dark matter can't get so close to it. Okay, so there may be sprinkles of dark matter being sucked in, but that amount is tiny compared to quarks. That's why you can't escape that.
Okay. I'm worried about tidal forces. Oh,
Sorry.
yes?
We're just going to take 4 more questions.
Oh, okay. I'm worried about tidal forces. I've heard that if you start falling towards a black hole of a few solar masses, that before you get to the event horizon, you die because you're torn apart by the tidal forces, that your feet and head are stretched apart. And, but if you have a very massive black hole, the tidal forces, I think, would be less because they're like, you know, m over r cubed and so on. So how massive does a black hole have to be before you can live through falling through the event horizon?
Right, that's a very good question. So you saw the event horizon scales linearly with the mass.
Yeah.
Okay, but the tidal radius is different. So there is no tidal radius that's smaller than the event horizon.
Yeah.
Okay, but your worry is very well-founded in the sense that, in fact, there are stars, as you saw, in our Galata Center that get so close to the black hole. Not the ones I showed. Those are on very regular orbits. But those of you who follow the news may know there was this object, a gas cloud called G2, that had been giving out flares in very energetic wavelengths, X-rays and gamma rays. That's believed to be a torn-off star, you know, that's being tidally disrupted by the 4 million solar mass black holes. And a lot of my colleagues have written papers about the next time the G2 will flare up, and I think it was believed to happen last month. And so far, no one has seen anything yet. So there must be some, you know, there are a lot of freedom in the calculations. So back to the tidal force, and you're absolutely right. If you were to fall through the event horizon, the gravity, tidal force is the difference between the force on your foot and your head, right? The difference. So you would want to make yourself, you would want to curl up to be as small as possible to reduce the tidal force. But even when you reduce yourself to the size of an atom, you're still going to get torn up.
Yeah, okay. Now, 2 black holes are orbiting. Don't they radiate gravitational waves until they finally spiral in and merge?
Absolutely. Only the very, very last few spirals, that's when the distortion of space-time is big enough to emit gravity waves, and that's what LIGO and pulsar timing experiments are all going after. That's a very, very important, it would be a very important verification of general relativity.
How can an item be so big to be squished down and still have a huge event horizon? Like, how can a star be squished to, like, 10 billion solar masses? That's a really strange concept, isn't it? It's gravity, really. It's incredible. I mean, gravity is attractive. Okay, there's not like the electrons and electrons, they repulse each other. Gravity has only one sign, and it's attractive. So the reason the sun is not shrinking, okay, is not because the gravity is not strong enough, but it's because at the center there is this opposite force, pressure, okay, that's resisting the collapse of gravity. So right now the sun is very happily sitting here because these 2 forces balance each other. But the moment when the central fuel, hydrogen, helium, get used up, that pressure will disappear, and gravity always wins. When there's no pressure, resisting that gravity is just going to pull things in. And if you don't stop it, it will become a black hole. Wait, so there's a really big, so is it just a really big star that made the supermassive black hole? Or what was it?
The supermassive black, that's a very good question. We don't, so I talked about the massive stars, the 14.8 billion solar mass, 14.8 solar mass object as the death of a massive star, okay? The origin of supermassive black hole is unclear right now. Perhaps there was a collection of stars that all collapsed together. You got to form the individual massive stars first, but somehow they were collected together in the early universe. Another theory is maybe you have a cloud of, say, 100,000 solar mass, a gas cloud, itself collapsed into an individual
supermassive black hole. And these two theories are competing with each other, and we don't have enough observational evidence to refute or prove each other one. But that's a great question.
Can black holes be created from antimatter?
No, the answer is no, in the sense that antimatter is just ordinary matter with the same mass, but opposite quantum numbers. Okay, so electron has an antimatter called positron. So antimatter left alone, they're happily living there. So there could be galaxy out there that's completely made of antimatter, except anytime you put ordinary matter around it, what antimatter love to do is to annihilate. Okay, PET scan. What does P stand for? PET, PET scan. It stands for positron. It's the antimatter of electron. And we use positrons and electrons, they annihilate each other and they give a huge flash of gamma rays, energetic photons. So you can't really hide, I mean, in fact, positrons are a tracer of, strange cells in our body by giving out light. So unless you can change that, you can convert that light into a black hole, which we don't know how to, there is no direct relation between antimatter and black hole.
Thank you.
Yes. Stephen Hawking has stated that black holes aren't really black, and they will eventually lose their mass and disappear. Can you comment on that?
Sure. So that's called the Hawking radiation, and that is a very important energy loss mechanism for tiny, tiny black holes. So the time scale for that to happen goes inversely proportional to very high power of the mass of your object. Okay, so these black holes I'm talking about, Hawking radiation occurs, but occurs at such a minute scale that it's not even going to matter over the age of the universe. Okay, so it's for very, very tiny black holes. I'm talking about primordial black holes, which we have no evidence of. That can evaporate through Hawking radiation. So right now, that's a theoretical conjecture, and these astrophysical black holes just don't, I mean, Hawking radiation is irrelevant.
Thank you very much for a heroic demonstration of how to explain these difficult objects. Thank you all for coming. Have a great summer. We hope to see you next fall.